Hey, welcome back. Tonight, we're talking about something most of us will never see with our own eyes. A planet so far away, so impossibly distant, that the light reaching it from the sun feels like a whisper compared to what we experience here on Earth. Neptune. It's the kind of world that rewards patience, curiosity, and a willingness to stare at the unknown without needing immediate answers. So before we go any further, like the video if you find yourself drawn to these stories about the edges of our solar system. Subscribe if you're the kind of person who wants to understand how the universe actually works. And let me know in the comments where you're watching from and what made you interested in Neptune specifically. It's always fascinating to see who's curious about the distant planets. Now dim the lights if you can, turn off the noise, and let's take a journey out to the farthest regions of our solar system, where the sun is barely a pinprick of light, and weather patterns defy everything we think we know about physics. Nobody had ever seen Neptune, not really seen it, not looked at it through instruments and recognized what they were looking at. The planet existed somewhere beyond the calculations and suspicions of astronomers, moving through space in patterns that made perfect mathematical sense to no one at all. This was the late 18th century, and the solar system was supposed to be understood by now. We had maps, we had telescopes, we had Newton's laws, which explained motion and gravity with almost religious precision. And then Uranus started to misbehave. When William Herschel discovered Uranus in 1781, it felt like the final frontier of the solar system had been reached. Here was a planet beyond Saturn, another world waiting in the darkness, confirming that the solar system extended further than anyone had thought. Nobody had imagined a planet could be hiding that far from the sun. Saturn had been the known boundary, the edge of the known solar system. Everything beyond that was speculation and myth. But Uranus was real. It was there. It had been observed, catalogued, measured. The solar system was bigger than anyone had believed, but Uranus wasn't cooperative. It didn't move where it was supposed to move. Astronomers calculated its orbit based on the gravitational pull of the sun and the other known planets, and Uranus consistently deviated from these predictions. Sometimes it was ahead of where it should be. Sometimes it lagged behind. The deviations were small individually, but they accumulated. Year after year of observations, position after position, the pattern became undeniable. These weren't tiny discrepancies that could be written off as measurement error or instrumental limitations. These were persistent, measurable, undeniable deviations that accumulated over years of careful observation. The scientific community faced a problem that felt almost insulting. They understood gravity. They understood mathematics. They had the tools. Yet a planet was refusing to behave according to expectation. Something was wrong, or rather, something was missing. Some invisible influence was tugging at Uranus, pulling it off course, disturbing its path through the void. The question was simple, but profound. What could be heavy enough, massive enough, to alter the orbit of an entire planet? What celestial body could be hiding in the darkness, unseen but measurable through its gravitational effects on something we could actually observe? Astronomers debated the possibilities. Some suggested that perhaps the calculations were wrong, that Newton's laws didn't apply as cleanly at these distances. Others wondered if there was some massive cloud of matter, some cosmic debris scattered in Uranus's orbit that was gradually slowing it down. But the more carefully the data was examined, the more it became clear that something systematic was at work. Something massive, something distant, something real. Enter Urbain, Joseph Leverrier. He was a French mathematician, precise and methodical, the kind of man who believed that if you understood the equations well enough, the universe would surrender its secrets. His mind worked differently from most astronomers. Where others looked at the sky and tried to interpret what they saw, Leverrier took what was observed and reversed the process. He didn't try to predict where Uranus should be based on gravitational theory. He observed where Uranus actually was, compared it to where it should have been, noted the precise deviations, and asked the universe to explain itself. What force was causing this? What object was exerting this gravitational pull? What could be hiding in the darkness beyond Uranus? Leverrier did not set out to discover a planet. He set out to solve a problem. He took the observed deviations of Uranus and worked backward through mathematics that would have seemed almost unimaginably complex to earlier generations. The calculations were staggering in their scope and difficulty. If this planet was being pulled by something, what would that something need to be? Where would it need to be positioned in space? What mass would it require to exert just the right gravitational influence to produce exactly these observed deviations? No more, no less. The equations had to balance perfectly. The mathematics had to account for every known force, every known mass in the solar system, and then deduce what was missing. The mathematics was elegant and brutal. Leverrier was relentless in his work. He calculated and recalculated obsessively. He refined his equations. He accounted for every known factor, every possible variable that might affect Uranus's orbit. The gravitational pull of the Sun, obviously. The gravitational pull of each known planet. The mass of each body, calculated as precisely as possible. The orbital mechanics. The three-body problem and its extensions. And gradually, from the mathematics, a picture emerged from the numbers. There should be a planet at approximately this position, with approximately this mass, in approximately this orbit. The precision of his prediction was extraordinary. He wasn't saying the planet was somewhere beyond Saturn, somewhere vague in the outer darkness. He was saying it was here, at these specific coordinates, at these celestial longitudes and latitudes, with these specific characteristics. He gave numbers, real numbers, measurable, verifiable, testable numbers. He didn't have a telescope. He didn't have the means to search the sky himself. That was the limitation of his time. He was a mathematician working at his desk with pencil and paper and pure intellectual power, deriving consequences from equations, extracting truth from symbols and numbers. So he sent his predictions to Johann Gottfried Galle at the Berlin Observatory, a man who did have access to the tools needed to actually look at the sky. Galle received Leverrier's letter. The prediction was audacious, almost absurd. Search this section of sky for a planet that no one had ever seen before, based on mathematical calculations about something already invisible. Verify this prediction. Find this world that exists only on paper. It went against the grain of how astronomy had always been practiced, from observation toward understanding. Astronomers had always looked first and understood second. They observed phenomena and then tried to develop theories to explain them. This was working in the opposite direction entirely. This was prediction preceding observation, mathematics leading the way, theory reaching out into the darkness to pull reality into alignment with its expectations. It was an extraordinary claim. It required an extraordinary amount of faith in the power of mathematics. But Galle was a careful observer. He trusted mathematics. He had seen what mathematics could do. He trusted precision. He trusted the work of a fellow scientist, even one separated from him by distance and nationality. They were part of a community of scientists, a shared endeavour to understand the universe. On the night of September 23rd, 1846, Galle pointed his telescope at the location Leverrier had specified. The telescope was good, but not extraordinary. The conditions were favourable, but not perfect. He was sceptical, but prepared. He was ready to be disappointed, to find nothing, to have to report that the mathematics had failed. But he was also ready to witness something extraordinary if the mathematics held true. He was ready for something remarkable. That same night, on the first night of searching, Gal found it, a new point of light that moved when it shouldn't. A celestial body exactly where the mathematics said it should be. Neptune. The planet had been found not through the patient observation of the night sky over years or decades, but through pure intellectual work. A mathematician in France had deduced the existence of a world on the other side of the solar system using nothing but mathematics and the laws of gravity. It was one of the great triumphs of human intellect, a moment when science proved it could predict reality rather than just describe it. It proved that the universe followed rules so fundamental, so consistent, that they could be discovered through thought alone. Galler sent back a confirmation. The planet is there. The mathematics held. The prediction was correct. Within days, the news spread across Europe, across the scientific world. There was a celebration in the discovery, a recognition that humanity had just accomplished something that seemed almost impossible. We had looked at something we couldn't see and determined what it was and where it was, all without ever laying eyes on it until after the mathematics had guided us to it. 17 days later, on October 10th, 1846, William Lassell discovered Neptune's largest moon, Triton, orbiting so close that it seemed almost to embrace the planet itself. Another discovery, another world revealed. Triton was massive, nearly half the diameter of Earth's moon, and it moved in a retrograde orbit, backward against the direction Neptune itself was rotating. An unusual moon with unusual characteristics, but secondary to the main discovery. The real victory belonged to Leverrier and to the idea that mathematics could reach across empty space and pull down the unknown. Neptune wasn't just a planet that happened to exist. It was proof that human understanding of the universe had reached a level of sophistication that could predict the existence of worlds without ever seeing them. It was proof that the universe was knowable, but Neptune itself remained a profound mystery. It was there. It had been found. It existed in the mathematical equations and astronomical observations. It appeared as a tiny point of light when observed through telescopes, yet nobody knew what it actually was. Nobody knew what kind of world it might be, what it was made of, what weather patterns might rage across its invisible surface, what secrets it held in its depths. All that remained was distance and darkness. The planet itself was a puzzle waiting to be solved, a mystery waiting to be unraveled. And the solving of that puzzle would require more than mathematics. It would require patience, better instruments, more detailed observations, and the kind of determination that accepts that answers might take generations to arrive. Neptune had been predicted and found. But truly knowing Neptune, understanding what it was and how it worked, was a challenge that would stretch across more than a century. Neptune sits at an average distance of 2.8 billion miles from the Sun. That's roughly 4.5 billion kilometers, 30 astronomical units away from our home star, where one astronomical unit is the distance from Earth to the Sun, which itself is 93 million miles. The numbers themselves are almost meaningless because they're too large to visualize. They exceed comprehension. They exceed the ability of the human mind to form a mental picture. You can say the words, you can write the numbers, you can type them into a calculator, but your mind doesn't have a framework for understanding what those numbers actually mean in physical terms. The distance between Earth and Neptune is so vast that light, traveling at its maximum speed, the fastest thing we know about, takes more than 4 hours to cross that gap. 4 hours. The fastest human-made object, Voyager 1, traveling at 38,000 miles per hour, would take more than 3,000 years to cover that distance. 3,000 years. That's longer than recorded human history. That's the distance we're talking about. Distance becomes abstract. Space becomes theoretical. So let me try a different approach. Try this instead. Imagine you're standing in the noon sunlight on Earth right now. The sun overhead is bright, warm, and immediate. The light is here. The warmth is here against your skin. It's the most obvious thing in the sky, the most undeniable presence you can imagine. Now imagine that you travel to Neptune. It's noon there too, by some arbitrary standard. You're looking up at the sun. But the light is so dim, so faint, that it feels like twilight. Not the romantic twilight of Earth's sunset with its warm oranges and purples. Not the gentle transition between day and night. A deep, grey twilight, where colours fade and the world becomes shades of grey. You can still see your hand in front of your face, but only barely. The details blur. The warmth is almost non-existent. The sun is just another star in the sky, one that happens to be slightly brighter than the others, but infinitely far away. That's the light available to Neptune. That's the sun that has shaped Neptune's entire existence. Earth receives roughly 900 times as much sunlight as Neptune does. 900 times. Imagine how much dimmer everything is when you divide the sun's light by that number. When you take the entire output of a star and spread it across the enormous distance between Earth and Neptune. The sun, which dominates our sky, is reduced to an afterthought in Neptune's sky. A bright star, but nothing more. Neptune had to wait a very long time to be seen in any detail at all. For more than 100 years after its discovery, the planet remained nothing but a point of light in the sky. A distant world that could be observed through increasingly sophisticated telescopes, measured and catalogued and mapped in position, but never truly understood. The deviations of Uranus had led to Neptune's discovery, but Neptune itself was far too distant, far too faint to reveal the details of what it actually was. You could see it was blue, you could measure its position, you could determine its orbital characteristics, but you couldn't see what was happening there. You couldn't see the weather, you couldn't see the storms, you couldn't understand what made it different from the other gas giants. The first spacecraft to reach Neptune was Voyager 2, which began its journey toward the outer solar system in 1977 and didn't encounter Neptune until 1989. 12 years. 12 years of travel through the emptiness of space. 12 years of carrying instruments and cameras toward a destination that most people didn't think about, toward a world that seemed too remote, too irrelevant to matter in any practical sense. The mission was expensive. Politicians questioned the funding. Scientists debated whether the money might be better spent on projects closer to home. There was no obvious benefit to visiting Neptune. There was no resource to extract, no material to acquire, no wealth to gain. It was pure science, pure curiosity, pure desire to understand. And yet it continued, year after year, traveling outward at incredible speeds, moving deeper into the solar system, heading toward a rendezvous with the unknown that many wouldn't live to see completed. But when Voyager 2 finally arrived in August of 1989, when it finally got close enough to see details, when the instruments could actually resolve the planet into something more than a blur, Neptune revealed itself as one of the most extraordinary and enigmatic places in the solar system. Neptune exposed itself as a world far more complex and far more mysterious than anyone had expected. Photographs came back. Data streamed across the solar system. The signal took more than 4 hours to reach Earth, traveling at the speed of light, carrying information gathered by cameras and instruments that had traveled farther than any human artifact before or since. Scientists who had spent their entire careers studying planetary science found themselves surprised by what the data owed. Colleagues who had devoted decades to understanding the outer solar system were seeing details they had never anticipated, weather patterns they couldn't fully explain, characteristics that didn't fit into the existing models. This was what exploration felt like. Not the confirmation of expected findings, but the discovery of the unexpected. Not the vindication of theories, but the revelation that the universe was stranger and more interesting than theories had suggested. Blue. That was the first thing everyone noticed when the photographs appeared on screens and were printed in scientific journals. Not a pale blue like Uranus. Not a muted or washed-out blue that might be understandable given how little light reached that world. A vivid, almost electric blue that seemed to glow from within. The color was striking, unexpected, and in some ways it changed how people thought about Neptune. A world that had existed only as mathematics and distant points of light for over a century was suddenly revealed to be colored, textured, dynamic, and alive in ways no one had fully anticipated. The images showed a sphere of blue surrounded by white clouds and dark storms. It was beautiful. It was strange. It was undeniably real. The blue itself was mysterious. Early scientists looking at those first images thought it might be related to some unknown chemical compound in Neptune's atmosphere. They theorized about exotic materials, about gases that might not exist anywhere else in the solar system. They speculated about substances that only formed under the extreme pressure and temperature conditions of Neptune's depths. Exotic chemistry operating at scales and conditions found nowhere on Earth. But gradually, through careful analysis and spectroscopy, through breaking down the light into its component wavelengths, the answer became clearer. Methane. Just methane, a simple hydrocarbon that existed in much smaller quantities elsewhere in the solar system. CH4, 4 hydrogen atoms bonded to one carbon atom, the same molecule that occurs naturally in Earth's atmosphere, that leaks from swamps and termite mounds, that powers some of our vehicles. Methane in Neptune's hydrogen and helium-rich atmosphere absorbed the red wavelengths of visible light and scattered the blue light back into space. The red wavelengths were absorbed, converting that energy to heat. The blue wavelengths bounced off particles and travelled back toward space, back toward waiting instruments, back toward Earth. It was elegant in its simplicity, but it also raised more questions than it answered. Why was Neptune's blue so vivid? Why was it so much more striking than the blue of Uranus, which had even more methane in its atmosphere? Uranus had higher concentrations of methane, yet it displayed a much paler, greenish tint, almost washed out compared to Neptune's vivid electric blue. It shouldn't have been that way. The answer lay in atmosphere clarity. Neptune was better at clearing its skies. The winds churned up methane gas from the depths, and those winds also helped sweep away haze and aerosol particles that would otherwise dim the colour. Haze rained out as snow, as strange as that sounded. Methane snow, or perhaps methane rain, falling from the clouds in a form no Earth meteorologist had ever witnessed. Neptune maintained its clarity through motion, through constant activity, through the kind of violent weather that kept the atmosphere clean and visible. So Neptune's blue was partly a function of its chemistry and partly a function of its weather. A world that was actively moving, actively mixing, actively maintaining the vivid colour that made it so visually distinctive. A world that refused to be dull or dormant. A world that maintained the appearance of vitality and energy through the very processes that made it so deadly and extreme. The images from Voyager 2 showed swirling patterns, weather systems, and cloud formations that suggested Neptune was anything but a dead, static world. There were storms visible at the cloud tops, swirling masses that dwarfed Earth. The Great Dark Spot, when Voyager 2 encountered it in August of 1989, was a storm system so massive that the entire Earth could fit inside it with room to spare. Dark regions that looked like holes into deeper atmospheric layers, windows through which instruments could see into darker hidden places. Bright clouds that seemed to float at the edges of larger storm systems, white wisps against the blue background, and scientists realized these might be crystals of frozen methane or ammonia, condensed out of the atmosphere and forming clouds in a world so cold that such things were possible. The planet looked turbulent, chaotic, and violently dynamic. The atmosphere had structure and depth, with different cloud layers at different altitudes, moving at different speeds, which was strange, deeply strange, because Neptune was so far from the Sun that there shouldn't have been enough energy to drive such extreme weather. The Sun's light was too dim to heat the atmosphere effectively. The solar wind was too weak to push clouds around. The radiation pressure from the Sun's light was negligible. By all logical reasoning, Neptune should have been a cold, dormant world, slowly radiating away the remnants of heat left over from its formation billions of years ago. It should have been a place of stillness and decay. But Neptune wasn't dormant. It was alive in ways that challenged fundamental understanding of planetary physics. It was a world that defied expectation. Neptune's winds are the fastest in the solar system. Not Jupiter's winds, which are powerful and famous, but somewhat more constrained by Jupiter's enormous size and mass. Not Saturn's winds, which are violent but still exist within limits, imposed by that planet's rotation and energy balance. Neptune's winds reach speeds of almost 2,200 kilometers per hour. Let that number sit for a moment. 2,200 kilometers per hour. That's around 1,300 miles per hour if you prefer imperial measurements. It's faster than the speed of sound. It's hypersonic. It's the kind of wind that doesn't just move things. It obliterates them. To put that in perspective, the most powerful hurricanes on Earth reach wind speeds of about 300 kilometers per hour at their strongest. 100 kilometers per hour is considered dangerous, the threshold where the wind starts to cause real structural damage to buildings, where it becomes unsafe to drive a car, where loose objects become projectiles. Neptune's wind speeds are more than 7 times faster than the most extreme Earth hurricane. 7 times faster. 7 times more violent. And these aren't localized phenomena, brief storms that come and go. These are sustained wind patterns that encircle the entire planet. They're roughly 3 times faster than Jupiter's most powerful winds, even though Jupiter receives far more solar energy. Jupiter is closer to the Sun. Jupiter is massive, a true giant that dwarfs Neptune. And yet Neptune's winds are faster, more violent, more extreme. And Neptune is 30 times farther from the Sun than Earth is. 30 times farther. The distance is staggering. It was a contradiction that puzzled astronomers for decades after Voyager 2's images came back. How could this be? Where was the energy coming from? What could possibly fuel such violent winds when the Sun's light was so dim it barely registered as a source of warmth? Where was Neptune getting the energy to maintain these wind speeds? Scientists looked at Jupiter and Saturn and understood their weather systems. The Sun heated the atmosphere, creating temperature gradients. Temperature differences between different latitudes drove wind systems. Convection in the upper atmosphere generated storms and maintained circulation patterns. All of it made logical sense. Energy in, weather patterns out. The Sun provided the energy source. Everything flowed from that fundamental reality. Neptune broke that model entirely. Neptune violated the assumptions that had made sense for every other planet in the solar system. The answer seemed to lie in Neptune's interior. The planet itself was generating heat, not just residual heat from its formation, not just a slow cooling process. More heat, actually, than it received from the Sun. Neptune radiates roughly twice as much warmth as it receives from solar radiation. Neptune takes in the faint sunlight that reaches it at such a great distance, and then radiates back out twice as much energy in the form of heat. That means the planet is producing internal energy somewhere deep inside its core. Energy that's being transported upward through the layers of the atmosphere and manifesting as these extraordinarily powerful winds. But where was that heat coming from? And how was it being channeled into wind patterns that were so violent, so consistent, so dominant that they could be measured and mapped and predicted? Some scientists theorized that Neptune had retained vast amounts of primordial heat from its formation billions of years ago. When the solar system was young, when planets were still accumulating material and growing through collision and gravity, that process generated enormous amounts of heat. Collisions released energy. Gravitational compression heated the interior. The young Earth was a molten world. Mars was molten. Venus was molten. Neptune too must have been extraordinarily hot. Neptune, being massive, had enough material and enough internal insulation to trap that heat effectively. The thickness of the atmosphere, the density of the interior, the sheer size all combined to create a thermal blanket that prevented heat from escaping quickly. And now, billions of years later, it was still radiating away that ancient heat, slowly cooling through an extraordinarily long timescale. Some estimates suggested it might take tens of billions of years for Neptune to cool to the point where it reached the same temperature as the space around it. An impossibly long time, longer than the current age of the universe. Others suggested that there might be ongoing processes in Neptune's interior, chemical reactions or gravitational compression, that continue to generate heat even now. The planet might be in some state of slow contraction, its internal structure still settling and compressing under its own immense gravity, converting gravitational potential energy into thermal energy. This was known as the Kelvin-Helmholtz mechanism, a process that released energy not through fusion, but through gradual compression. It was a controversial idea because it required Neptune to still be contracting, still be changing fundamentally. Some speculated more dramatically that there might be an ocean of superheated water beneath the visible clouds, trapped at those depths by the immense pressure, slowly releasing energy that manifested as wind and weather. The idea was almost poetic, a hidden ocean of hot water, unseen and unmeasured, driving the most extreme weather in the solar system from depths that no probe had ever reached. The pressure at those depths was so extreme that water would exist in states unknown on Earth, in exotic phases of matter that defied simple categorization. Solid ice, but also somehow fluid. Water that was as much rock as liquid. The physics became strange at those scales. The composition of Neptune's atmosphere was relatively simple, at least on the surface. Primarily hydrogen, around 80%, the lightest element, the first element ever created in the universe. Helium at about 20%, the second lightest element. And then trace amounts of other compounds. Methane, which provided the color, ammonia, hydrogen sulfide, water ice crystals. Methane dominated the clouds, visible from above, creating the blue coloration. But deeper down, in regions of higher pressure and temperature, other substances dominated. Scientists believed that far below the visible clouds, in a region nobody had directly observed, there might be clouds of ammonia ice crystals. Deeper still, clouds of hydrogen sulfide. And deeper still, clouds of water ice. The atmosphere tended down through layers of increasing pressure and temperature, and each layer had different composition, different properties, different characteristics. The truth was, nobody really knew what Neptune was made of at its core. Nobody had ever been there. The pressure was so extreme that it would crush any probe humanity had ever built, crush it like it was tissue paper. The Voyager spacecraft had collected data from a distance, had measured radiation, had taken photographs, but had never actually descended through the atmosphere. Neptune remained largely unexplored, visited by only a single spacecraft that flew past in the span of a few hours before accelerating onward toward the edge of the solar system and beyond. A world that received barely enough light to see its surface clearly, that generated its own heat, and that channeled that heat into weather patterns that defied easy explanation. Every answer led to more questions. Every observer. Tian suggested that Neptune was more complex, more energetic, more fundamentally strange than anyone had initially imagined. It was a world that had been predicted by mathematics and found by calculation, proof of the power of human intellect. But truly understanding it, grasping how it worked, comprehending the mechanisms that drove its winds and maintained its energy, remained beyond the reach of current science. The greatest minds in astronomy and planetary science continued to puzzle over Neptune's mysteries. Neptune kept its secrets. It hid them beneath those blue clouds, beneath layers of atmosphere that no human would ever touch, beneath pressures and temperatures that made such visitation impossible with any technology we currently possessed or could imagine possessing. Neptune was distant, not just in space, but in knowledge. It existed at the edge of what we could understand, at the boundary between the known and the unknown. And in many ways, the greatest mystery was that this distant, frozen, apparently inhospitable world was alive in ways that defied expectation. A world of wind and weather and heat and energy, existing in the darkness at the edge of the solar system. A world that demanded understanding, even as it resisted it. That puzzle of internal heat was more than just an intellectual curiosity. It was a direct challenge to how scientists thought planetary systems worked. Energy comes from somewhere. It doesn't appear from nothing. The universe doesn't reward mystery with free power. But Neptune seemed to violate that fundamental rule. The planet was radiating roughly twice as much energy as it received from the sun. Twice as much. Take a moment and think about that. The sun was so distant, so weak in its delivery of light and warmth, that it barely registered as a source of energy at Neptune's distance. The sunlight arriving at Neptune was roughly 900 times dimmer than the light Earth receives. 900 times. Yet somehow Neptune was taking that minimal energy input and channeling it into wind patterns that exceeded anything Jupiter could produce. More than that, the planet was generating its own heat, releasing it into space at a rate that doubled the already minimal solar input. Where was that heat coming from? When Voyager 2's instruments measured Neptune's thermal radiation, the data seemed almost wrong at first. Scientists had to check the instruments. They had to verify the calibrations. They had to make sure the spacecraft itself wasn't producing the heat through some instrumental artifact. But the measurements were accurate. Neptune was definitely radiating more energy than it received. The total power output was measured in watts, enormous numbers that expressed the sheer scale of what was happening inside the planet. Every second, Neptune was radiating more energy than all of humanity consumed in a year. Every second. That continuous output meant something inside the planet was generating heat. Something was converting potential energy into thermal energy at a prodigious rate. The question was what, and the answer remained fundamentally mysterious. The most straightforward answer was that Neptune had retained primordial heat from its formation. When the solar system was young, only a few billion years after the Big Bang itself, when planets were still assembling themselves from colliding debris and dust, gravity was releasing enormous amounts of energy. Everything was crashing together. Planetary embryos were colliding with each other at speeds that would vaporize material on impact. Every collision, every merger of smaller bodies into larger ones, generated heat through friction and gravitational compression. The kinetic energy of impacts was converted directly into thermal energy. The infalling material would heat to incredible temperatures. The young Earth had been molten, covered in magma seas. So had Venus, so had Mars. Neptune, being far more massive than any of those worlds, would have been extraordinarily hot when it first formed. It would have been glowing in the darkness, radiating thermal energy into the void of space, cooling slowly as its formation completed, and the bombardment of material gradually ceased. That heat didn't disappear instantly. It persisted. A massive planet like Neptune has enormous thermal inertia. It's difficult to heat up and equally difficult to cool down. The layers of atmosphere and the thickness of the interior create insulation. Think of the planet as an enormous flywheel of thermal energy, slowly dissipating what was put into it during formation. Heat conducts outward from the interior, moving through rocky material in the mantle and then through the atmosphere before radiating into space. But heat conduction is slow. It takes time for thermal energy to move through material. The distance from Neptune's core to its surface is vast, thousands of kilometers. Heat traveling that distance at the speed at which heat conducts through rock takes an extraordinarily long time. The heat from Neptune's formation might have remained trapped inside for billions of years, slowly radiating away into the cold void of space, at a rate that was imperceptible in human terms, but measurable over geological timescales. Scientists did the calculations. How long would it take a planet the size of Neptune to cool from its initial molten state to its current conditions? The math suggested tens of billions of years, perhaps longer. Some estimates suggested that Neptune wouldn't reach thermal equilibrium with its surroundings, wouldn't stop radiating excess heat for longer than the current age of the universe, which was itself about 13.8 billion years old. The planet might be 4.5 billion years old and still not finish cooling from its formation. The thermal lifetime of Neptune was measured in timescales that exceeded the lifetime of stars, like Earth's own sun. That seemed almost absurd. The idea that heat from the moment of creation could still be driving the weather systems visible today felt like discovering a fossil from before the continents formed, still walking around alive. It felt like finding an ancient fire still burning inside a world that had had billions of years to cool. Yet the physics held up. The numbers worked. The calculations checked out when performed by independent researchers using different methods and assumptions. Neptune was a world that was still, in a sense, warm from birth, retaining memory of the violent process that had created it, still dissipating energy from that ancient cataclysm. But there was a complication. Not all scientists accepted that ancient heat alone could explain what was observed. Some argued that continued internal processes might still be generating new heat. Neptune might not be a static world slowly cooling down. It might be a dynamic world where ongoing changes in the interior continued to release energy. Perhaps there was ongoing gravitational compression. The planet's interior might still be contracting slightly under its own weight, converting gravitational potential energy into heat. This process, called Kelvin-Helmholtz contraction, could sustain energy release without requiring heat from the original formation to persist. It was a process that had been proposed by 19th century physicists trying to understand the source of the sun's energy before nuclear fusion was discovered. For the sun, it turned out to be a dead end. Fusion was the true source. But for Neptune, Kelvin-Helmholtz contraction might still be operational. Even a tiny amount of contraction over billions of years, gradual settling of material under gravity, could release enormous amounts of energy. Or perhaps the source was chemical. Reactions happening in Neptune's interior might still be releasing energy. The chemistry of exotic matter under extreme pressure might be generating heat continuously. Compounds that were stable at Earth's pressures might break down or reform under Neptune's extreme conditions, releasing or absorbing energy in the process. Or perhaps there were reactions between different materials that hadn't fully equilibrated yet, still slowly reacting toward their final states, releasing energy in the process. The chemistry at those pressures was so exotic that most reactions had never been observed or measured under any human-controlled conditions. The interior of Neptune was a chemical experiment that nobody could conduct directly, a reaction vessel so extreme that all we could do was observe the end products and try to infer what was happening inside. The most speculative theory suggested an ocean of superheated water beneath the visible clouds. This wasn't water as Earth knew it. It wasn't liquid water that could be drunk or swum in. The pressure at those depths was so extreme that water existed in phases unknown on Earth. Superionic ice was real enough to have been demonstrated in laboratories by striking ice with powerful lasers, subjecting it to pressures analogous to those found in Neptune's interior. Under the right pressure and temperature conditions, ice could exist in a state that was partially solid and partially fluid simultaneously. The crystal structure remained, the atoms maintaining their lattice positions, but the protons, the hydrogen nuclei, could move freely through the solid oxygen framework. The protons would diffuse through the structure like ions in a liquid, carrying electrical charge, conducting electricity, transferring heat. It was strange matter, neither quite solid nor quite liquid, existing in a realm of physics that required extreme conditions to understand. Laboratory experiments showed that superionic ice could exist over a range of pressures and temperatures. A phase diagram that suggested vast regions of Neptune's interior might be filled with this exotic form of water. That ocean, hidden beneath Neptune's clouds, was theorized to be extremely hot. Temperatures might exceed thousands of degrees Celsius, hot enough to melt metals, yet still constrained to remain liquid or solid by the incomprehensible pressure. Not boiling away because the pressure kept it locked inside, holding it compressed, preventing the phase transition to vapor. The same force that prevented it from evaporating kept it from freezing. The pressure so intense that normal melting points were altered completely. It existed in a balance point where heat, pressure, and the phase transitions of matter all aligned, a region of phase space that existed nowhere on Earth, that only existed in Neptune's depths. And if that ocean was releasing heat through convection, through large-scale motion of hot material rising and cool material sinking, that might explain where Neptune's energy came from. The planet itself might be like a heat engine, with the internal ocean driving currents that transported thermal energy upward, and those currents channeling that energy into the overlying atmosphere where it manifested as wind and weather. The ocean might be churning, stirring, moving material around, and in that motion, internal heat would be transported outward, eventually reaching the visible atmosphere and driving the winds observed from outside. None of this could be confirmed. No probe had ever descended into Neptune's interior. No instrument had ever directly measured the temperatures at those depths. The pressure would crush any device humans could build. The heat would destroy it. All of this was inference based on observations made from a distance, calculations performed using physical laws, and models constructed to fit the data. But the models were internally consistent. They explained the observations. They made predictions that could potentially be tested by future missions, if such missions could ever be conceived and funded and built and launched. For now, Neptune kept its energy source secret. The mystery deepened when scientists looked at Neptune's magnetic field. Here was another puzzle that refused to fit neatly into existing frameworks. A magnetic field is generated by moving charged particles. On Earth, the outer core of molten iron circulates, and that motion creates our magnetic field, a consequence of the Coriolis effect and the motion of liquid metal in a rapidly rotating environment. Jupiter's magnetic field is generated by a layer of metallic hydrogen deep in its interior, hydrogen compressed to such extreme pressures that it becomes an electrical conductor, and the rotation of that conductive layer generates the planet's magnetic field. The magnetic field is a consequence of motion in an electrically conductive fluid. Neptune's magnetic field presented a problem that defied easy explanation. The planet's magnetic axis was tilted about 47 degrees from its rotation axis. The magnetic pole was not at the same location as the geographic pole. For Earth, the difference is only about 10 degrees, a small angle that's been gradually changing over the centuries. For Neptune, it was nearly 50. Imagine if your planet's magnetic field was tilted almost at a right angle to the direction it was spinning. That's what Neptune looked like, a configuration that seemed almost deliberately designed to confuse astronomers and planetary physicists. More problematic still, the magnetic pole wasn't even at the center of the planet. It was offset. The magnetic center was displaced from the planetary center, buried somewhere off to one side, like having a magnet that wasn't aligned with the center of the sphere you were trying to magnetize. This meant that as Neptune rotated, its magnetic field underwent wild variations. Radio signals fluctuated dramatically, cycling up and down as the tilted magnetic pole swept past observation points. The magnetosphere, the region of space around Neptune influenced by its magnetic field, would undergo dramatic swings and surges as the planet turned. The magnetic field strength at any given point in space would increase and decrease with each rotation as the tilted magnetic axis swept around. Every rotation brought a wild ride of changing magnetic conditions, a pulsing, oscillating environment that would be catastrophic for any spacecraft attempting to navigate it. This was fundamentally different from Jupiter and Saturn, whose magnetic fields were more orderly and aligned relatively closely with their rotation axes, creating more stable magnetospheres that didn't undergo these wild gyrations. Uranus had a similarly tilted magnetic field, almost as extreme as Neptune's, tilted about 60 degrees from its rotation axis. Both ice giants seemed to violate the rules that applied to the larger gas giants, suggesting that there was something fundamentally different about how these smaller, colder worlds generated their magnetic fields. Scientists trying to understand Neptune's magnetic field had to deal with an uncomfortable question. Where was the magnetic field actually being generated? For Jupiter and Saturn, the source was clearly the core, the central region where conditions were extreme enough to create exotic matter that conducted electricity. Jupiter's metallic hydrogen, Saturn's potentially exotic ice-rocky core, both would be deeply buried, centrally located, and generate magnetic fields that were roughly centered on the planet's axis. For Neptune, the source appeared to be somewhere in the mantle, a region of superionic ice that was neither fully solid nor fully liquid, distributed throughout a thick layer that extended across much of the planet's interior. This ice was crystalline in structure, but also somehow fluid in its properties. The ions that made up this material, the protons and oxygen nuclei, could move through the crystal structure of their own matrix, and that movement of ions, moving charged particles through a region that extended over thousands of kilometers, could generate a magnetic field. The circulation pattern of ions would create electrical currents, and those currents would generate a magnetic field through the same physics that made electromagnets work. But a magnetic field generated in the mantle would behave differently than one generated in the core. It would be less stable. It would undergo more dramatic variations. It might naturally have its axis tilted relative to the rotation axis. It might naturally be offset from the planetary center rather than centered at it. Neptune's magnetic field wasn't a failure of the planet's magnetic properties or a sign that something was broken. It was just different. It was a consequence of having the source of magnetic generation located where it was, in material that existed in a strange physical state, at pressures and temperatures that made it neither quite solid nor quite liquid. The tilted, offset magnetic field made sense if you understood where it was coming from. The implications were unsettling in a subtle way. If Neptune's core wasn't generating the magnetic field, then what was the core actually made of? Was it rock, metal, some combination of the two? Nobody knew. The core of Neptune was further away, physically and conceptually, than the center of the Earth was from a person standing on the surface. The pressure was incomprehensibly extreme. The temperature was unknown. Whatever was there was fundamentally alien to human experience. It existed at conditions that human physics could barely describe, and human technology could never directly observe. The magnetic field mysteries pointed to a deeper truth about Neptune. It was a world fundamentally strange in ways that defied easy categorization. It didn't behave like Jupiter. It didn't behave like Uranus. It had properties all its own, generated by physical conditions that existed nowhere else in the solar system. Beneath those blue clouds, beneath the layers of visible atmosphere where methane ice crystals drifted and reflected light back towards space, beneath the regions where winds of 2,000 kilometers per hour tore through the air in patterns that seemed almost incomprehensibly violent, beneath all of that lay something profoundly unknown. The atmosphere extended to depths where pressure and temperature both became extreme, exceeding anything in Earth's experience. At some depth, perhaps hundreds of kilometers down, the distinction between atmosphere and interior blurred. Gas became compressed beyond the point where it remained gaseous. Density increased relentlessly. Matter existed in states that required entirely new terminology to describe accurately. Scientists couldn't simply call it gas or liquid or solid. It was something in between, something that combined properties of multiple states of matter simultaneously. Scientists believed there were layers to Neptune's interior, distinct regions with different properties and compositions, though the exact location of boundaries between layers remained unknown. In the upper atmosphere, methane dominated, providing the blue color that defined Neptune's appearance. Below that, ammonia clouds might drift at various altitudes, forming in regions where temperature and pressure allowed ammonia molecules to condense into solid or liquid droplets. Further down, hydrogen sulfide clouds might form at depths where that compound could condense. Each layer was colder than the one above, a temperature gradient stretching downward. Each layer was denser than the one above, a density increasing inexorably with depth. Eventually, cold ceased to be the right description because the temperature began to increase again as you descended deeper. Temperature simply became a number, indicating the speed of molecular motion, in material that was increasingly exotic and c'est-à-dire, existing in forms that Earth-based chemistry had no names for. At some depth, somewhere between the cloud layers and the molten core, the atmosphere gave way to something denser. Liquid water, perhaps mixed with ammonia and methane in proportions that depended on temperature and pressure at each depth, might exist as a vast ocean beneath the clouds. This ocean wouldn't be anything like Earth's oceans, wouldn't resemble the terrestrial seas in any meaningful way. No light penetrated here. None of the visible light that made Earth's oceans visible. No chemical reactions analogous to those on Earth were possible. No photosynthesis, no oxygen production, no food chains dependent on sunlight. Life, as humans understood it, dependent on liquid water, organic chemistry, and energy from chemical reactions or sunlight, could not exist in those conditions. But the ocean would be there nonetheless. A vast mass of water under such pressure that it existed in unusual states, far denser than liquid water on Earth, would be at those pressures, perhaps with properties that would seem strange if experienced directly. The density would increase with depth, the pressure would increase with depth, the temperature would increase with depth. all variables pointing toward. Deconditions more and more extreme. Beneath that ocean, farther down, lay the core. Rock and metal mixed together, compressed into a solid mass by the weight of everything above it. The core of Neptune might be multiple times more massive than Earth, a sphere of dense matter the size of Earth, or larger, hidden under layers of atmosphere and ocean and superionic ice. Temperature at the core might exceed 15,000 Celsius, hot enough to glow, exceeding the surface temperature of the Sun, which was only 5,500 Celsius. The pressure might be millions of times greater than Earth's atmospheric pressure at sea level, pressures that human minds could barely grasp, forces so intense that they could alter the fundamental properties of matter. This interior was theoretically known through models and calculations, but practically unknown through observation. No human would ever see it. No device would ever reach it intact. The core of Neptune would remain hidden, maintaining its secrets, existing in isolation at the bottom of a world that refused to reveal itself. Yet the existence of that core, the presence of those hidden depths, had to explain Neptune's behavior. It had to explain the heat. It had to explain the magnetic field. It had to explain why this distant world, so far from the Sun that it received barely any solar energy, was so dynamically active and complex. Neptune's ring system was discovered so recently that older photographs of the planet, taken by telescopes in the 19th and early 20th centuries, simply missed them entirely. They weren't hidden through any deliberate concealment or through any fundamental limitation in how telescopes worked. They were simply faint and dark, composed of materials that reflected very little light, difficult to see against the background of space. The rings existed as real physical objects orbiting the planet, and astronomers had been pointing telescopes at Neptune for more than a century after its discovery, carefully mapping the planet and searching for companions and satellites. But the rings remained invisible until the 1980s, when a clever new observational technique revealed them. This technique, called stellar occultation, involved watching a star as it passed behind Neptune and its rings, analyzing the way the starlight flickered as it was blocked by the rings. The flicker in pattern revealed structures that conventional telescopes had failed to directly image. When a star is gradually blocked by a ring, its light doesn't simply vanish. It flickers and oscillates as individual particles in the ring pass in front of the star, creating a pattern that reveals the structure and composition of the ring itself. The technique required precise observations and careful timing, but it worked. And in 1984, scientists announced the discovery of Neptune's ring system. When Voyager 2 flew past Neptune in August of 1989, it finally obtained the first direct images of the rings, close-up photographs that revealed details no ground-based telescope could ever observe. 5 main rings existed, all named after astronomers who had made significant contributions to humanity's understanding of Neptune. Galle, Leverrier, Lassell, Arago, and Adams spread out from the planet in thin bands of material arranged at varying distances. The rings were nothing like Saturn's magnificent, spectacular system, the iconic rings that appeared in textbooks and photographs as one of the most beautiful features in the solar system. Saturn's rings were made primarily of ice, water ice in chunks ranging from centimeters to meters in size, brilliant white material that reflected sunlight effectively. Neptune's rings were dark, composed of rocky material and dust mixed together, dark organic compounds that reflected very little light. Some regions of the rings contained up to 70% dust by mass, a powder of fine particles. Dust particles, smaller than a micrometer in size, like the finest talc or smoke, floated alongside larger fragments of rock ranging up to meters or larger. The rings appeared almost black against the dark of space, nearly invisible, visible only when struck directly by sunlight, or when blocking starlight behind them. Light barely reflected from them. They were subtle, understated, almost apologetic about their existence compared to the dramatic, visible from Earth rings of Saturn. The rings were also thought to be young, geologically speaking, far younger than Saturn's rings, which were believed to be nearly as old as the solar system itself. Neptune's rings might not have existed for billions of years like the planets themselves. They might have formed relatively recently, within the last few 100 million years, or even less. The exact age was difficult to determine since no probe had ever collected samples from the rings. The source was uncertain, a matter of ongoing debate and speculation. Perhaps a small moon had strayed too close to Neptune and been torn apart by tidal forces. The moon passing inside what was called the Roche limit, where the planet's gravity would stretch an object until it disintegrated. Perhaps a comet had collided with an existing moon at high velocity, destroying it and scattering its debris across space, where some of it was captured by Neptune's gravity and fell into orbit around the planet. Perhaps two moons had collided with each other, destroying both and creating the debris field. Whatever the origin, the rings now existed as a collection of debris slowly orbiting the planet, slowly being perturbed by gravity and collisions, gradually destined to either fall into the planet and burn up, or be scattered into space and become independent objects, or perhaps somehow remain in orbit for billions of years more. But something strange happened in the outermost ring, the Adam's ring. The material didn't spread evenly around the planet as expected. Instead, it clumped into arcs, incomplete rings, segments of orbit that contained the bulk of the ring material, while other regions of the same orbit were nearly empty. 4 prominent arcs had been named Liberté, Égalité, Fraternité, and Courage, bearing names that reflected the French discovery team's poetic inclination and their desire to encode a message of freedom and brotherhood into the solar system itself. These arcs were puzzling because they shouldn't exist according to the laws of orbital mechanics. Orbital mechanics, the branch of physics that describes how objects move in gravitational fields, predicted that particles in these locations should gradually spread around the entire orbit over time. Collisions between particles would scatter them in different directions. The gravitational pull of the planet would perturb their orbits. Over a reasonable timescale, perhaps a few million years, they should form a complete ring, spreading material evenly around the entire orbit. Yet the arcs remained concentrated, stable, refusing to disperse. Something was keeping them together. Something was preventing them from spreading. Something was actively maintaining them in a configuration that defied equilibrium. The answer was found in the gravity of a small moon called Galatea, orbiting just inside the Adam's ring. Galatea's gravity was pulling on the particles in the arcs, constraining them, keeping them concentrated in specific regions. The moon's gravity would resonate with particles in certain orbital locations, either accelerating them or decelerating them, pulling them back if they tried to drift away from the arc. The effect was called shepherding, a concept where small moons act like shepherds, using gravity to keep particles gathered together rather than letting them scatter. Shepherding had been proposed to explain the rings of Saturn and Uranus, and now Neptune's arcs confirmed the concept applied to multiple planetary ring systems. This discovery led to a deeper understanding of how rings could be maintained across timescales that exceeded human experience. Neptune's rings might have been older than initially thought, sustained through billions of years by the gravitational effects of shepherd moons. But the moons themselves might have been captured from elsewhere. They might have been asteroids or comets that wandered into Neptune's gravity well from the Kuiper belt or the asteroid belt and became permanent residents of Neptune's system. Or they might have formed in place from the same collisional events that created the rings themselves. The system was complex, with multiple processes occurring simultaneously throughout the ring's history. Particles collided with each other and were knocked into different orbits, either escaping the ring system or settling into new stable configurations. Moons provided gravitational guidance, shepherding particular rings into ordered configurations and maintaining those configurations against the forces that would otherwise scatter them. New particles were created when larger objects fragmented from impacts or collisions, adding fresh material to the rings. Older particles were lost when they fell into the planet and were destroyed by heat and friction, or when they escaped to space and became independent bodies. It was an active system, constantly changing, yet maintaining enough stability that the rings were observable and measurable across centuries of observation by humans. The ring system of Neptune represented, in miniature, the processes occurring throughout the planet's vicinity. Gravity organized chaos, structure emerged from debris. Order appeared to arise from disorder, though the order was always temporary, always destined to change. The rings were transient features in cosmic timescales, present today, but potentially absent millions of years hence, when some particles had fallen into the planet and others had escaped to become independent objects. Yet they existed now, visible proof that even at Neptune, at the edge of the solar system, in a place so distant that sunlight barely reached it, so isolated from the inner solar system that human missions would take decades to reach it, structure and organization still occurred. The universe was not entirely chaos at these distant reaches. Pattern emerged from the application of physical laws. Complexity arose from the simple interactions of gravity and the momentum of moving particles. And in that emergence of complexity from simplicity, in the organization of scattered debris into discernible rings, in the shepherding of fragments into stable arcs that shouldn't exist but did, lay a hint of something fundamental about how the cosmos worked. Even at Neptune, even in darkness, even in isolation at the edge of the solar system, the same laws that governed planets and stars operated, creating order, maintaining structure, sustaining complexity. The universe, even in its most extreme and distant reaches, was not random or lawless. It was governed, organized, structured, and comprehensible. Neptune's rings, faint and dark though they were, provided yet another example of the cosmos, revealing its secrets to those willing to look. But the rings were not Neptune's only moons, and they were not even close to being its most interesting ones. Beyond the shepherds and the ring systems, a family of smaller moons orbited the planet in various states of chaos and order. These were the lesser satellites, the companions that had somehow been captured or had formed in the distant past and persisted, orbiting a world so far from the sun that no earthly telescope could see them without significant technological assistance. They were real nonetheless, present, measurable, and in several cases profoundly strange in their own right. The system of Neptune was not simple, not a world with a handful of companions. It was complex, layered, filled with objects of varying sizes performing their gravitational dance. Some moons orbited close to the planet. Others orbited at greater distances. Some were small enough to fit inside a terrestrial city. Others were large enough to be worlds in their own right. All of them, together, formed a complete system, a gravitational network that had persisted for billions of years. The discovery of Neptune's moons happened in stages spread across centuries. Triton, the largest, was found just 17 days after Neptune itself was discovered in 1846. William Lassell discovered it almost immediately, recognizing that Neptune had a substantial satellite. The discovery was remarkable not because it was unexpected, but because of how quickly it was found. Neptune was a new world, barely known to human observers, and already astronomers were discovering companions. Other moons came later, after telescopes had improved, after observation techniques had advanced. Miranda was discovered in 1949. Proteus wasn't found until 1989, just days before Voyager 2's encounter with Neptune. The discovery of Proteus was particularly late because the moon was so faint that it had remained hidden despite centuries of observations from Earth. It took a spacecraft flying millions of kilometers to finally image it clearly. Triton was different from the other moons because it was genuinely massive. It was the largest moon orbiting Neptune, a world in its own right, a sphere of ice and rock large enough to be rounded by its own gravity. At 2,710 kilometers in diameter, Triton was smaller than Earth's moon, but larger than Pluto. It was substantial enough that if it orbited the Sun independently, it would be classified as a dwarf planet, a world significant enough to demand serious study. The composition was unusual. Triton was not a rocky terrestrial body like Earth's moon. It was primarily ice, with the ice being water ice, mixed together with other frozen substances. Methane ice, nitrogen ice, perhaps carbon dioxide ice as well. The exact proportions were difficult to determine from observations alone, but scientists estimated that about 30 to 45% of Triton's mass was water ice, with the remainder being rocky material and metal. This composition suggested an origin somewhere in the outer solar system, perhaps in the Kuiper Belt, that region of icy bodies orbiting the Sun beyond Neptune's orbit. The evidence for Triton's alien origin was compelling. Triton moved backwards around Neptune, orbiting in the opposite direction to Neptune's rotation. This retrograde orbit was unusual. Most moons orbit in the same direction as their primary planet rotates. Captured during the early solar system, when they formed from the same disk of material, or when they were gently captured by gravity, retrograde orbits suggested a different origin. They suggested an object that had wandered into the gravitational well of Neptune from outside, perhaps from the Kuiper Belt or from interplanetary space, and been captured by the planet's gravity after traveling in a direction opposite to Neptune's natural rotation. Triton was likely a captured object, a wanderer from elsewhere that had been pulled into Neptune's gravitational embrace and forced into orbit. The fact that it had survived this capture process, that it hadn't been torn apart by tidal forces or crashed into Neptune's atmosphere, was itself remarkable. The capture would have been violent, a dramatic encounter where Neptune's gravity overcame the object's velocity and trajectory, pulling it into orbit. The tidal stresses during that capture would have been enormous, potentially melting parts of the object, redistributing its mass, deforming it fundamentally. Yet Triton survived. It settled into a stable orbit. It persisted. This suggested that Triton had been substantial, massive enough to withstand the forces of capture, rigid enough to resist complete destruction. A smaller object might not have survived. A less massive object might have been torn apart. But Triton was large enough and strong enough to endure the violence of capture and emerge intact, altered but functional, a new satellite of Neptune, bound now to the planet by gravity, orbiting in the opposite direction to the planet's rotation, a permanent marker of an encounter billions of years in the past. The future of Triton was calculated and grim. The tidal forces between Neptune and Triton were not balanced. Triton was slowly spiraling inward toward Neptune. The orbit was decaying, the distance between moon and planet gradually decreasing. The calculations showed that in approximately 3.6 billion years, Triton would reach what was called the Roche limit, the closest distance to Neptune that a moon held together only by its own gravity could survive. At that point, Neptune's tidal forces would overcome Triton's self-gravity. The moon would be torn apart. It would disintegrate into fragments, pieces of ice and rock scattered across space. Some of those fragments would fall into Neptune's atmosphere and burn up. Others would remain in orbit around Neptune, becoming a new ring system, a replacement for the current rings that were themselves destined to gradually dissipate. or fall into the planet over billions of years. This prediction meant that Neptune was currently in the process of acquiring a new ring system. The process was extraordinarily slow, measured in billions of years, but it was happening nonetheless. Triton was doom-bound. The moon's fate was sealed by orbital mechanics, by the mathematics of gravity and the physics of tidal forces. There was no escape, no possibility of avoidance. In the far future, Neptune would destroy its largest moon and inherit new rings. The transformation would be dramatic, altering the appearance of the planet system in ways that would be unrecognizable to observers today. But that transformation remained in the distant future, far beyond the lifetime of any human civilization that might ever exist. For now, Triton persisted. It orbited Neptune with a thin atmosphere, a ghostly halo of gas surrounding the moon's surface. This atmosphere was incredibly sparse, so thin that if you stood on Triton's surface, you would not feel the atmosphere at all. The pressure was measured in microbars, trillions of times less than Earth's atmospheric pressure at sea level. The atmosphere was so thin that it was technically measurable, but practically negligible. Yet it existed. It was composed primarily of nitrogen, with some methane, and perhaps traces of carbon dioxide. This atmosphere had been detected by Voyager 2 as the spacecraft passed by Triton, measured by instruments that were sensitive enough to register even this incredibly tenuous gas. The surface of Triton was cold, so cold that the numbers seemed almost incomprehensible. The temperature was measured at -235 degrees Celsius or -391 degrees Fahrenheit. This was colder than any other measured place in the solar system. The cold was so extreme that nitrogen, methane, and carbon dioxide all existed as frozen solids on Triton's surface. These were substances that were gases on Earth, at Earth temperatures and pressures. But here, on Triton, they froze solid. They formed ices, solid surfaces, frosts covering the moon's landscape. If you brought liquid nitrogen from Earth, -196 degrees Celsius, and left it on Triton's surface, it would freeze solid. Triton was colder than liquid nitrogen. It was cold in a way that transcended normal human experience or intuition. This extreme cold should have meant a dead, static surface, a landscape frozen in place and unchanging. But observations revealed something different. Triton had a young surface by solar system standards. The rarity of impact craters suggested that the surface had been reshaped relatively recently, perhaps within the last few billion years. Something had been renewing Triton's surface, erasing ancient impacts, creating a landscape that appeared young, despite the moon being nearly as old as the solar system itself. The mechanism for this renewal was extraordinary. Triton had active geysers. On a world so cold that nitrogen was a solid, geysers erupted from the surface, shooting ice and gas upward into space. When Voyager 2 flew past Triton in 1989, its cameras captured images of these geysers in action. Plumes of material, nitrogen and dust and perhaps other volatiles, were blasting upward at speeds that would carry them kilometers into Triton's thin atmosphere. One plume was measured to be over 5 kilometers high, an enormous eruption of frozen material bursting from the surface in a world where everything was supposed to be locked in place by cold. The mechanism driving these geysers was mysterious. How could geysers erupt on such a cold surface? Where was the heat coming from? The leading theory suggested that the geysers were powered by nitrogen and methane ice. Beneath Triton's surface, in the interior of the moon, there was residual heat, perhaps primordial heat retained from the moon's formation, perhaps heat generated by tidal friction as Triton's gravity and Neptune's gravity constantly pulled and tugged at the moon's interior. That heat was sufficient to create pockets of liquid nitrogen or methane beneath the surface. When pressure increased, or when some trigger caused the liquid to vaporize suddenly, the gas would escape explosively, creating the geysers. It was a process analogous to geysers on Earth, like Old Faithful in Yellowstone, but powered by exotic substances rather than water, and occurring on a moon so cold that the geothermal energy required was far smaller than what would be needed for terrestrial geysers. The surface features of Triton were equally strange. A large region of the moon's mid-latitudes was covered in terrain that was nicknamed cantaloupe terrain because of its appearance. It looked like the dimpled, wrinkled surface of a cantaloupe melon, with ridges and valleys arranged in patterns that suggested unusual geological processes. The exact mechanism that created this terrain remained unknown. It might result from repeated cycles of freezing and thawing, from subsurface convection of icy materials, or from other cryogenic processes that operated on a scale difficult for humans to comprehend. The cantaloupe terrain covered a substantial portion of Triton, tens of thousands of square kilometers of dimpled, wrinkled surface, a region so distinctive and unusual that it defined a significant part of the moon's appearance. Whatever process had created it was ongoing, perhaps, or had been very recent in geological terms, recent enough that the features had not yet been erased by impacts or other surface processes. Another region of Triton featured broad, featureless plains dotted with massive calderas, the depression structures formed by volcanic or cryovolcanic collapse. These features indicated that volcanic activity, though of an exotic ice-based variety, had occurred across much of Triton despite the extreme cold. The calderas were enormous, some of them hundreds of kilometers across, vast depressions in the surface where material had been removed, either erupted outward or collapsed inward. These were not small features. They were planetary-scale structures, evidence of substantial geological activity at some point in Triton's history. The southern hemisphere of Triton was dominated by a vast nitrogen ice cap, an accumulation of frozen nitrogen at the South Pole. This ice cap was dotted with dozens of cryovolcanoes, the vents from which the geysers erupted. The cryovolcanoes were not localized to a small region. They were spread across the ice cap, suggesting that volcanic activity was widespread, that heat from Triton's interior was reaching the surface across a substantial area of the moon. The landscape appeared alien, strange beyond easy description, a world that seemed to violate the basic assumptions about how planetary surfaces should behave in such extreme conditions. Triton was not a dead world. It was not a frozen, static, unchanging place. It was active, dynamic, geologically alive in ways that seemed almost impossible given the temperatures and the isolation. But Triton was not alone in Neptune's system. Smaller moons orbited the planet, caught in various orbits, performing their silent dance around the world they were bound to. Proteus was the second largest moon, a chunky, irregular body that moved in a relatively close orbit to Neptune. Proteus was discovered late, in 1989, because it was faint and difficult to detect from Earth. It was roughly 210 kilometers across, a substantial moon by solar system standards, but still only about 8% the size of Triton. Proteus had an irregular shape, not rounded into a sphere by its own gravity the way Triton was. Instead, it appeared to be a jumbled mass of rock, perhaps the remnant of a collision between two larger bodies, or perhaps a captured asteroid. The surface was heavily cratered, marked by impacts that had pummeled the moon over billions of years. Then there were the smaller moons. Nereid orbited Neptune at a distance, in an eccentric orbit that brought it relatively close to the planet at times and then swung it far away. The orbit was unusual, not circular like most moons, but elongated, carrying Nereid on a path that ranged dramatically in distance. The nature of Nereid's orbit suggested an origin different from most other moons. It might be a captured object like Triton, though orbiting in the usual prograde direction. Larissa orbited closer to Neptune, one of several small moons that persisted in the inner reaches of Neptune's system. At roughly 200 kilometers across, Larissa was small but substantial. A chunky, irregular body, much like Proteus. Larissa had been discovered in 1989 by Voyager 2, along with several other small moons, previously unknown to science. Galatea was the shepherd moon, the object whose gravity maintained the ring arcs, the force that prevented the ring particles from dispersing. Despina orbited inside the rings, possibly helping to confine them or interact with them gravitationally. Thalassa and Naiad were discovered late, their orbits and characteristics remaining somewhat uncertain even after Voyager 2's observations. These moons, particularly the smaller ones, were poorly known. They were difficult to observe from Earth. Limited data existed about their compositions, their exact sizes, their precise orbits. Much remained to be learned about them. These moons, collectively, formed a system of companions orbiting Neptune, a collection of objects that had been captured or formed in the distant past and persisted to the present day, silently orbiting a world so far from the sun that direct sunlight there was barely distinguishable from darkness. The complete family of Neptune was complex, layered, diverse. Some moons were large enough to be called worlds. Others were barely more than rubble piles held together by weak gravity. Some orbited close to the planet, exposed to substantial tidal forces. Others orbited far away, relatively stable in their orbits, removed from the most intense gravitational effects of the planet. This diversity suggested a complex history, a system that had not formed in a single event, but had accumulated objects, over billions of years. Capture events brought new bodies. Collisions destroyed or altered existing moons. Gravitational interactions shuffled the system, adjusted orbits, created the current configuration. The current state of Neptune's satellite system was a snapshot, a moment in time, a configuration that was temporary and would change given enough time. The lesser moons were discoveries made over centuries, each one revealing something new about Neptune's system. They were not as impressive as Triton, not as spectacular as the rings, but they were important nonetheless. They represented the complete family of Neptune, the complete system of satellites and rings that orbited the planet. Together, they created a gravitational environment, an ecosystem of orbits that interacted with each other, that influenced each other, that had evolved over the entire history of the solar system. Some moons had been captured, others had formed in place. Some were destined to spiral into Neptune in the distant future. Others would persist for billions of years more. But all of them were part of Neptune's story, part of the complete picture of what this distant world was like, how it functioned, what orbited around it in the darkness at the edge of the solar system. For most of human history, Neptune's moons and rings remained unknown. No human eye could see them without technological assistance. No telescope developed before the 20th century could detect them clearly. Neptune itself was invisible to unaided vision, a planet that existed beyond the reach of human perception for thousands of years of recorded human history. The solar system was incomplete in human understanding. Uranus was the outermost planet known to ancient and medieval astronomers. Beyond that lay only speculation and mathematical theory. Then in 1846, Neptune was discovered through mathematics, through prediction rather than observation. And within days, Triton was found, orbiting the newly discovered planet, waiting for human attention, waiting for the moment when human technology would finally be capable of detecting it. The discovery of Neptune was transformative for human knowledge. It proved that the solar system extended farther than previously known. It demonstrated the power of mathematical physics, the ability to predict celestial phenomena without directly observing them. It opened the question of what lay beyond. Were there more planets, more moons, more worlds waiting in the darkness beyond Neptune's orbit? For over a century after Neptune's discovery, observation of the planet and its system remained limited to Earth-based telescopes. The distance was enormous. The light was faint. Details were difficult to resolve. Astronomers made observations, recorded them, compiled data, but their knowledge remained limited. They knew Neptune had a large moon called Triton. They had discovered other satellites more gradually. They had observed the planet's weather, its colors, its behavior. But they did not truly know Neptune. They could not see its surface clearly. They could not measure its exact dimensions accurately. They could not determine the composition of its atmosphere with precision. They were looking at a world from billions of kilometers away, trying to understand it through telescopes that magnified light and attempted to resolve details that were impossibly distant. Then in 1977, something changed. A spacecraft left Earth, heading outward into the solar system on a mission to explore the giant planets. Voyager 1 was its name, and its initial target was Jupiter and Saturn. But there was a second spacecraft, Voyager 2, which was designed to explore Jupiter and Saturn as well, and perhaps, if the mission succeeded and the spacecraft remained functional, to continue onward toward the outer planets. Voyager 2 would eventually become the only spacecraft ever to visit Neptune. It would fly past the planet and its moons, gathering data at close range, taking photographs, measuring temperatures, analyzing atmospheres. It would be humanity's first, and for the foreseeable future, only direct encounter with Neptune. The Voyager program was ambitious beyond measure. 2 spacecraft, sent in different directions, both capable of surviving years or decades of travel through the solar system, both equipped with instruments to measure and observe worlds never before visited at close range by human technology. The mission was designed to take advantage of a rare alignment of the planets, a configuration that would not occur again for 176 years. The trajectory would allow Voyager 2 to visit not just Jupiter and Saturn, but Uranus and Neptune as well, a grand tour of the outer solar system that would never be repeated during any human lifetime alive in that era. The engineering required was extraordinary. The spacecraft had to be designed to operate reliably after traveling for years without any possibility of repair or servicing. Power had to come from radioisotope thermoelectric generators, devices that converted the heat from radioactive decay into electricity, a method necessary because solar panels would not generate sufficient power at such immense distances from the sun. Communications had to function reliably across billions of kilometers, with signals taking hours to travel from Neptune to Earth. Computers had to process information with technology that was primitive by modern standards, but was cutting edge at the time. The instruments had to measure everything, from the composition of atmospheres, to the strength of magnetic fields, to the detailed topography of moons. Voyager 2 launched in 1977 and began its journey. It passed Jupiter in 1979, sending back images of that giant world and its system of moons and rings. It passed Saturn in 1981, revealing the complexity and beauty of that ringed planet. The mission was successful beyond expectations. The spacecraft survived the journey through the asteroids, through the radiation belts around the giant planets, through collisions with dust and debris. It transmitted data back to Earth across vast distances, data that revolutionized human understanding of the outer solar system. scientists and engineers on Earth navigated the spacecraft, adjusted its trajectory, managed its power consumption, kept it alive and functional. Every decision during those encounters had to be made with care, with awareness that a wrong command could disable systems or waste precious opportunities. The encounters lasted only days, but decisions made during those few days would have consequences that would ripple forward for decades, affecting the trajectory and course of human knowledge about the outer solar system. By 1989, Voyager 2 was approaching Neptune. It had travelled for 12 years since leaving Earth, had visited 2 giant planets and their systems, had sent back tens of thousands of photographs and measurements of unprecedented detail. Now, it was approaching the distant blue world at the edge of human knowledge. The approach was carefully planned. The spacecraft would pass near Triton, gathering close-up images and data on the Moon. It would measure Neptune's magnetic field, analyze its atmosphere, photograph its weather systems, study its rings and satellites. The spacecraft carried instruments that could measure ultraviolet light, infrared radiation, radio waves, and charged particles. It had cameras that could photograph objects billions of kilometers away. It had spectrometers that could analyze light and determine the composition of distant materials. It had magnetometers that could measure the strength and direction of magnetic fields. It had sensors that could detect radio emissions, thermal radiation, and the presence of plasma. Every instrument was designed to gather data during that brief encounter. For a few days, Neptune would be visited by human technology for the first time. Humanity would finally see this distant world at close range, a moment of direct contact that would provide more information than a century of Earth-based observations. The data that Voyager 2 gathered was transformative. The close-up images of Triton revealed a world unlike anything previously imagined. The geysers were photographed. The cantaloupe terrain was imaged. The surface features were mapped. The thin atmosphere was measured. Temperatures were recorded. Densities and compositions were determined. Simultaneously, Voyager 2 studied Neptune itself. It measured the wind speeds, confirming that Neptune's winds were the fastest in the solar system. It analyzed the atmosphere, revealing the composition of the gases. It photographed weather patterns, showing the Great Dark Spot and other cloud features. It measured the magnetic field, confirming its unusual tilted configuration. It discovered new moons. It imaged the rings. The amount of data Voyager 2 gathered was enormous. Gigabits of information, transmitted across billions of kilometers of space, received on Earth by radio telescopes, and processed by computers that were themselves primitive by modern standards. The spacecraft was moving at incredible speed, and the encounter with Neptune lasted only a few days. Everything had to be accomplished in that brief window of time. The photographs had to be taken. The measurements had to be made. The data had to be stored and transmitted. Once Voyager 2 passed Neptune, that opportunity was gone. There would be no second chance. The spacecraft would continue onward, into interstellar space, eventually leaving the solar system entirely. It would not return. It would not encounter any other planets. Neptune would be its final planetary encounter. The discoveries made during that encounter fundamentally changed human understanding of Neptune. Before Voyager 2, Neptune was known only from distant observations. It was a blur through telescopes, a point of light against the darkness of space. Astronomers knew it existed, knew it was a planet, knew it had satellites and perhaps rings, but those details were vague, uncertain, incomplete. After Voyager 2, Neptune was revealed. It was a world, a real place, with weather and geology and moons and rings. It was no longer a distant abstraction. It was a known world, visited by human technology, measured and observed and photographed. The encounter lasted only days, but it changed everything. It provided data that would fuel research and speculation for decades afterward. But the data also raised new questions. The geysers on Triton were surprising, unexpected, raising questions about the heat source and the mechanisms driving them. The strange retrograde orbit of Triton suggested an exotic origin, a captured moon from elsewhere. The wind patterns on Neptune were incomprehensible, given the minimal solar energy reaching the planet. The magnetic field was tilted in an unusual way. The rings were dark and faint, unlike the spectacular rings of Saturn. The Great Dark Spot was a surprise, a massive storm that would later vanish. All of these observations, all of this data, revealed a world far more complex and strange than anyone had anticipated. In the decades since Voyager 2's encounter, scientists have spent enormous effort analyzing and reanalyzing the data from that brief encounter. New discoveries have been made through data analysis. Technologies developed since 1989 have allowed scientists to extract more information from the Voyager data than was possible at the time of the original encounter. Computers have modeled Neptune's atmosphere, its dynamics, its weather. Theoretical physics has been applied to understanding the magnetic field, the interior heat, the geysers on Triton. Research has continued, driven by the data returned by Voyager 2, by the photographs taken during those few days of encounter. Yet there remain fundamental questions. How does Triton maintain its geysers in such extreme cold? What exactly is the composition of Neptune's interior? How do the winds of Neptune persist without sufficient solar energy? What is the source of Neptune's internal heat? These questions remain partially answered at best. Voyager 2 provided data, but that data was gathered during a brief encounter from a distance measured in thousands of kilometers at the closest approach. The data was detailed by the standards of the time, but limited by the capabilities of 1989 technology. More recent observations have come from Earth-based telescopes and from the Hubble Space Telescope, orbiting Earth in space, capable of observing Neptune across the vast distance. These observations have revealed changes in Neptune's weather patterns, variations in its appearance, evidence of seasons on the distant world. Scientists have documented variations in the intensity of storms, changes in cloud formations, shifts in atmospheric composition. The observations have shown that Neptune is not static, not unchanging despite the vast distance from the Sun. The planet continues to evolve, continues to change, continues to be dynamic. But these observations are limited by distance. The resolution is lower, the details are less clear. The information is valuable, but incomplete compared to what a direct encounter could provide. A spacecraft passing near Neptune could gather information 1,000 times more detailed than any Earth-based telescope. The differences in what could be learned are profound. The observation of Neptune from Earth has always been challenging. The planet is so distant that it appears as only a small dot through even large telescopes. Before photography, astronomers could only describe what they saw in sketches and notes, subjective interpretations of what could be resolved visually. Early photographic plates showed Neptune as barely more than a point of light, indistinguishable from bright stars except that it moved visibly across the night sky over the course of hours or days. Modern telescopes, including the Hubble Space Telescope, can resolve some details of Neptune's appearance. They can detect changes in cloud patterns. They can measure methane absorption in the atmosphere, observing how the planet's color shifts as the concentration of methane changes. They can observe variations in brightness, correlating changes in brightness with weather patterns and seasonal variations. But these observations are limited compared to the wealth of data that a spacecraft passing nearby could gather. A spacecraft at close range could see details invisible from Earth. It could measure temperatures directly, rather than inferring them from radiation measurements. It could photograph surface features of moons clearly, rather than as barely resolved specks. It could gather data that would answer questions and raise new ones. Neptune remains, in many ways, one of the least understood planets in the solar system. It has been visited by only one spacecraft. It has been observed from Earth for only about 175 years since its discovery. The body of knowledge about Neptune is growing, slowly, carefully, as scientists extract more information from available data and as new observations are made with improved telescopes. But Neptune still holds many secrets. The interior remains unknown. The exact source of the internal heat remains uncertain. The mechanisms driving the weather patterns remain incompletely understood. The system of moons and rings continues to evolve, continues to change, continues to reveal new information as decades pass and observations accumulate. Questions remain about how the system formed, how it evolved, how it will change in the future. The study of Neptune continues to the present day. Observatories on Earth continue to observe the planet, adding new observations to the archive of data accumulated over centuries. Observatories in space, freed from the distorting effects of Earth's atmosphere, continue to gather images and measurements. Archive data from Voyager 2 continues to be analyzed, reprocessed with new computer technologies that extract information that was not fully exploited when the data was originally gathered. Theoretical models continue to be refined, incorporating new observations and new understanding. Our understanding deepens slowly, carefully, incrementally. Neptune is no longer completely unknown, but it remains profoundly mysterious in many ways. It is a world that has been touched by human technology, visited by human spacecraft, observed by human instruments. Yet vast unknowns remain. The future may bring new spacecraft, new missions to Neptune, new opportunities to observe the planet at close range and gather data that could answer the questions that currently remain. A spacecraft passing through the Neptune system would answer questions that have remained open for decades. It would provide data about the interior, the composition, the dynamics of the atmosphere. It could land on Triton, gather samples, determine the source of the geysers. It could map the other moons in detail. It could study the rings from close range. But those missions lie in the future, and the future of space exploration is uncertain. Funding is limited. Priorities shift. Technology advances. For now, Neptune remains at the edge of human knowledge, a world simultaneously known and unknown, visited once by spacecraft and touched by human observation, waiting patiently for the next encounter that may never come during any lifetime currently alive on Earth. Yet beneath the question of whether we will ever return to Neptune lies something equally important, something that has been unfolding for decades across observations that were scattered, incomplete, difficult to interpret. Neptune is changing. The planet is not static. The seasons are shifting, and the evidence is there if you know how to look for it. Each year that passes brings data points that add to the picture, slowly, accumulating, revealing patterns that span decades rather than days or even years. The seasonal changes on Neptune are not like seasons on Earth. They do not arrive and depart within a year. They move at a pace that makes human lifespans seem almost negligible. Each season lasts for more than 40 years. Remember, a duration that means a single human being experiences only a fraction of a Neptunian season in their entire lifetime. Imagine seasons so long that the change from summer to autumn stretches across your childhood, your education, your early career, perhaps your middle age. By the time you are old enough to recognize the shift from autumn to winter, much of your life has already passed. This is Neptune's reality, a world where time itself moves at a different scale, where change happens with such slowness that detecting it requires patience, careful observation, and the willingness to track data across generations of scientists and decades of telescopes. The Neptunian year is 165 Earth years long. The planet takes 165 years to complete one full orbit around the Sun. Since Neptune was discovered in 1846, the planet has completed only a single orbit since human observation began. In 2011, Neptune returned to roughly the same position in its orbit that it occupied in 1846. That is the extent of our direct historical knowledge of Neptune's orbital cycle. We cannot yet claim to understand a full Neptunian year from direct observation. We have only lived through about 80% of one Neptunian year since discovering the planet. The seasons themselves are divided equally across this lengthy period. Spring lasts approximately 41 years. Summer lasts approximately 41 years. Autumn and winter follow suit, each stretching across 4 decades. When Neptune was discovered in 1846, the planet was transitioning out of autumn in its southern hemisphere and approaching winter. In 2011, when the planet completed its orbit, it had just exited winter and was entering spring again. The implications are staggering. Scientists studying Neptune today are observing a planet that has just completed one full seasonal cycle. For the first time since discovery, Neptune's atmosphere is being exposed to changing seasonal conditions that repeat patterns established more than 160 years ago. What changes might have accumulated? What differences might be apparent between the current spring and the spring that occurred before 1846? The evidence for seasonal change on Neptune has come largely from observations of atmospheric methane concentrations. Methane is a sensitive indicator of temperature and atmospheric dynamics. As Neptune's seasons shift, the distribution of methane throughout the atmosphere changes. During different seasonal phases, methane condenses out of the gas phase or evaporates back into it. Concentrations rise and fall, and these variations leave signatures that observers on Earth can detect. Telescopes have measured the brightness of Neptune in methane-sensitive wavelengths. The measurements show variations that correlate with Neptune's season. The planet appears brighter at certain times and dimmer at others. The change subtle but measurable with sufficiently sensitive instruments. The trend shows that Neptune has been gradually brightening over the past several decades, a change that some scientists interpret as evidence of seasonal shift. As the planet's atmosphere responds to the slow progression of seasons that have been underway for thousands of years already and will continue for thousands of years more, the brightening is not dramatic. The change in Neptune's observed brightness amounts to only a few % over several decades. Yet this is precisely what theorists would predict if seasonal changes are occurring. As Neptune's southern hemisphere approaches spring, more sunlight reaches that hemisphere. The increased illumination would be expected to alter cloud formation, change the distribution of methane, and alter the planet's overall reflectivity. The methane itself responds to seasonal temperature changes. When a hemisphere moves towards summer, the atmosphere warms. Warmer methane evaporates more readily, releasing more of the gas into the atmosphere. The increased methane concentration would affect how sunlight is reflected and scattered. More methane means more absorption of certain wavelengths and more scattering of others. The overall result is a change in how bright the planet appears when observed through methane-sensitive filters. Observers tracking Neptune's brightness in recent decades have documented a gradual increase, a trend that suggests the southern hemisphere has been warming as it transitions from winter towards spring. If this interpretation is correct, then Neptune's seasonal cycle is proceeding precisely as theory predicts. an enormous validation of the models that scientists use to understand planetary atmospheres. The changes are not dramatic. Neptune is not suddenly growing clouds or losing its atmosphere. The variations are modest, measured in percentages of brightness, variations that would be invisible to casual observation, but that become apparent when you track the data carefully over decades. This is the nature of Neptune's seasonal changes. They are real, they are happening, but they are happening at timescales that dwarf human experience, at rates that make it difficult to say with certainty whether you are observing a real trend or whether you are capturing only noise in measurements that are inherently imperfect. Scientists are divided on how to interpret the data. Some argue that the brightening of Neptune indicates seasonal change, that the planet's atmosphere is responding to seasonal variations just as theories predict. Others suggest that the observations might reflect variations in solar activity, changes in Earth's atmosphere that affect how observations are conducted, or other factors that complicate interpretation. The truth is probably that all of these effects are occurring simultaneously, layered on top of each other, making it difficult to isolate the specific signal of seasonal change. Yet the observations continue. Year by year, decade by decade, the data accumulates. Future observers, perhaps several centuries from now, will have sufficient data to determine with certainty whether the trends detected in the current era represent genuine seasonal change, or whether they were temporary fluctuations in a more complex system. For now, Neptune's seasons remain partially visible, partially mysterious, a phenomenon that science can barely detect but cannot fully understand. The seasonal question is inseparable from the larger mystery of Neptune's missing heat. This is perhaps the most pressing question about Neptune, the phenomenon that most sharply contradicts expectations and most clearly demonstrates how much remains unknown about the distant planet. Neptune radiates more heat than it receives from the Sun. The planet takes in solar energy, but the amount of energy it radiates back out into space is greater, approximately twice as much as it receives. This should not be possible according to simple energy conservation. Energy cannot be created. If Neptune is radiating more heat than it receives, that energy has to come from somewhere. The obvious explanation is that Neptune possesses internal heat, residual warmth left over from the planet's formation bill, ions of years ago, preserved somehow in the planet's interior and gradually escaping outward. But this explanation creates a secondary mystery. Neptune is supposed to be similar in many ways to Uranus. Both are ice giants. Both are at similar distances from the Sun. Both formed around the same time, from similar materials. Yet Neptune is hotter than Uranus. The temperature difference is dramatic. Neptune's interior is substantially warmer. Neptune radiates more heat. Neptune has more energetic weather patterns, more violent winds, more dynamic atmospheric activity. All of these differences suggest that Neptune possesses more internal heat than Uranus. But why? Both planets should have retained similar amounts of primordial heat. Both should have cooled at similar rates. Both should radiate energy at similar rates. The difference is unexpected and presently unexplained. Scientists have proposed various mechanisms that might explain Neptune's interior heat. One suggestion involves tidal heating. Triton, Neptune's largest moon, orbits the planet in a retrograde orbit. This retrograde orbit is dynamically unusual, unstable. Triton is slowly spiraling inward toward Neptune, its orbit decaying over billions of years. As Triton moves inward, it exerts tidal forces on Neptune. These tidal forces squeeze and distort Neptune's interior, deforming the planet slightly. The deformation involves friction. Friction generates heat. Perhaps, the theory goes, the tidal forces from Triton are sufficiently intense to generate heat at rates that help explain Neptune's excess energy emission. The problem with this theory is that the calculations suggest the tidal heating should be less than what is actually observed. Even accounting for Triton's gravitational effects, the heat generated does not fully match the heat that Neptune is radiating. Some other source of heat must be contributing to the total. Another possibility involves the internal structure of Neptune itself. Perhaps Neptune possesses a core, a rocky and metallic center similar to the cores of the other giant planets. If this core is more massive than expected, it might have retained more primordial heat. The core would be deeper inside Neptune, buried beneath layers of ice and exotic matter, insulated by kilometers of material surrounding it. The internal pressure at such depths would be extraordinary, high enough to compress any volatile ices into exotic states of matter, where the normal rules of physics are bent by extreme conditions. Perhaps beneath those layers of compressed ice lies a core that is still substantially hotter than the surrounding material, a region where temperatures are maintained at levels high enough to drive convection, to power weather systems, to generate the energy that Neptune radiates. But the actual composition of Neptune's interior is unknown. No spacecraft has ever penetrated Neptune's atmosphere. No seismic waves have been measured bouncing around Neptune's interior. All theories about what lies beneath the visible cloud layers are fundamentally speculative, educated guesses based on models and theory rather than direct observation. Yet another explanation involves the greenhouse effect. Neptune possesses a methane-rich atmosphere. Methane is an excellent absorber of infrared radiation. Infrared radiation is heat radiation, the form of energy that objects radiate away when they are warmed. If methane in Neptune's atmosphere is absorbing infrared radiation efficiently, it might trap heat that would otherwise escape to space. Internal heat generated deep within Neptune, attempting to radiate outward, encounters methane molecules. The methane absorbs the radiation and re-emits it, some of which is directed back downward toward the interior. This creates a heat trap, an insulating blanket that prevents internal heat from escaping as readily as it would without the methane. The effect would be similar to the greenhouse effect on Earth, where carbon dioxide and methane absorb infrared radiation and warm the atmosphere. Perhaps Neptune's methane is so efficient at trapping heat that the planet's interior remains warmer than theory predicts. Perhaps the combination of internal heat at Arceus, tidal heating from Triton, and the greenhouse effect of Neptune's methane-rich atmosphere together explain why Neptune radiates more heat than it receives. The problem is that none of these explanations is individually sufficient to account for the observed excess heat. Together, they might approach the total, but the arithmetic is uncertain, dependent on parameters that are not well measured, on properties of Neptune's interior that are not well known. This uncertainty leads to a profound realization. Neptune is a planet that we know in some ways quite well. We know its size, its distance from the Sun, its atmospheric composition. We know it has rings and moons and weather. We have observed it from Earth for almost 175 years since its discovery. We have visited it once with Voyager 2 and gathered unprecedented data. Yet in other ways, Neptune remains fundamentally mysterious. The interior is unknown. The source of the internal heat is unknown. The mechanisms driving the weather patterns are incompletely understood. The formation history is uncertain. Neptune is simultaneously well studied and profoundly enigmatic, a world that reveals details when examined, but keeps its fundamental secrets hidden. The comparison with Uranus makes the mystery more acute. Uranus is actually smaller and less massive than Neptune, yet Uranus is colder. Uranus radiates less heat than it receives from the Sun, exactly as theory predicts for distant ice giants. But Neptune is warmer and radiates more heat, a contradiction that stands out starkly when you place the two planets side by side. What happened to Neptune that did not happen to Uranus? Did Neptune undergo a collision billions of years ago that generated sufficient heat to alter its interior? Did Neptune migrate more violently than Uranus, scattering planetesimals and generating internal friction and heating? Did Neptune accumulate additional mass, drawing in more material and gaining more gravitational potential energy that converted to heat? Or did Neptune simply form in a different location where temperatures were higher, retaining that initial heat advantage even after migrating to its current position? The answers might be contained in the mathematical models that describe planetary migration and evolution, but those models remain uncertain, dependent on parameters that are not well constrained, on initial conditions that are not well known. The mystery of Neptune's heat extends into the deeper mystery of Neptune's origin. How Neptune formed, where it formed, what happened to it after formation. All of these questions remain partially unanswered. The current model of solar system formation, called the Nice model after the city in France where it was developed, suggests that the giant planets did not form where they currently orbit. Instead, they formed closer to the Sun in a more compact configuration. After formation, gravitational interactions between the planets caused them to migrate. Jupiter moved inward toward the Sun. Saturn moved inward as well, though not as much. Uranus and Neptune, the ice giants, migrated outward, away from the Sun, scattering planetesimals as they went, eventually settling into their current distant orbits. This migration model explains many features of the current solar system that are difficult to explain if the planets formed in their current positions. The Nice model has been refined repeatedly over the years as astronomers have gathered more data and computational power has increased. The model now includes multiple phases of planetary migration, periods of instability, followed by periods of relative stability. During the unstable periods, planets could have swapped positions, collided with one another, been gravitationally ejected from the system entirely. The model reproduces many features of the current solar system surprisingly well, including the distribution of planets, the spacing of their orbits, the existence and characteristics of the asteroid belt and the Kuiper belt. Yet uncertainties remain, particularly regarding the ice giants. Did Uranus and Neptune form at their current distances from the Sun? Did they form closer in and demigrate outward? Did they form at different distances from each other and then move to their current positions through gravitational interactions? Different scenarios would produce different outcomes for Neptune's interior heat, different expectations for its current properties. But Neptune's migration history is uncertain. Did Neptune migrate outward from a position closer to the Sun? By how much? Over what timescale? These questions affect how much heat Neptune should have retained from its formation. A planet that migrates gradually, in a stable manner, might retain more primordial heat than a planet that experiences violent gravitational encounters that heat its interior. A planet that migrates slowly might have a different internal structure than one that migrates quickly. The details matter, but the details are not known. The calculations become complicated quickly. You must account for gravitational interactions among all 4 giant planets simultaneously. You must model the scattering of planetesimals by the migrating planets. You must account for the disk of gas that surrounded the Sun during the early solar system, and that affected planetary migration through drag forces. You must consider how the planet's formation masses compared to their current masses. What material was accreted? What was ejected? The models that result are extraordinarily complex. dependent on dozens of parameters, some of which are not well constrained by observations. Small changes in initial conditions can produce dramatically different outcomes. There is also the question of Neptune's composition. Did Neptune form from the same materials as Uranus? If so, why is it hotter? Did it form in a different location, perhaps gathering different materials? Did it acquire additional mass through collisions that generated heat? The formation process for ice giants is itself poorly understood. Terrestrial planets like Earth form by accumulating material gradually, starting with dust and planetesimals, building up a core, accreting a rocky exterior, slowly adding mass until the planet is complete. Giant planets likely form differently, but the exact mechanism is debated. Did Jupiter and Saturn form by core accretion, where a rocky core accumulated first and then attracted a massive hydrogen and helium atmosphere? Or did they form by disk instability, where a portion of the protoplanetary disk became gravitationally unstable and collapsed directly into a planetary mass? The formation method would affect the composition, structure, and thermal history of the resulting planet. For ice giants like Neptune, the situation is even more uncertain. Neptune is much less massive than Jupiter and Saturn. If Neptune formed by the same mechanism, it should have accumulated less hydrogen and helium. But Neptune's composition does not match what simple models predict. Neptune appears to have more heavy elements, more water and methane and ammonia relative to hydrogen and helium than the simple models suggest. This compositional discrepancy suggests that either Neptune formed through a process different from what the current models assume, or Neptune formed at a different location and migrated there, or some other process altered Neptune after formation, removing some of its hydrogen and helium while enriching it in heavier elements. The puzzle remains incomplete. Science does not do well with incomplete puzzles. Scientists prefer certainty, clear answers, definitive explanations. Yet Neptune offers neither. Instead, it offers mysteries layered upon mysteries, questions that lead to other questions, a world that reveals itself gradually and reluctantly, a world that demands patience and careful observation. Perhaps in the future, another spacecraft will visit Neptune, breaking the 3.5-decade drought since Voyager 2 flew past. Perhaps that spacecraft will gather data that solves the mysteries, answers the questions, explains Neptune's interior heat and formation history. Or perhaps the visit will raise new questions, reveal new mysteries, deepen the puzzles further. History suggests the latter is more likely. Every time humans have visited a new world, every time a spacecraft has gathered close-up data on a previously distant object, the result has been an explosion of new knowledge accompanied by new mysteries. The Moon appeared to be a simple dead world from Earth. The Apollo missions revealed it to be complex, dynamic, with a history that was incompletely understood, even after direct exploration. Mars appeared to be a barren desert. Rovers have found evidence of past water, past atmospheres, past conditions. That might have supported life. Venus appeared to be a static hellscape. Detailed observations have revealed an active, changing world with active volcanism and rapidly cycling atmospheric phenomena. Neptune is following the same pattern. From Earth, it seemed relatively simple, a distant ice giant with some interesting features, but nothing that dramatically contradicted theoretical expectations. Voyager 2 revealed it to be far more complex, far more dynamic, far more mysterious than Earth-based observations had suggested. A new visit would surely deepen that complexity further. The future of Neptune exploration is uncertain in ways that reflect broader uncertainties about space exploration priorities and funding. Mars dominates current attention, The Moon is receiving renewed focus after decades of neglect. Europa, the icy moon of Jupiter, has become a target of interest because of the subsurface ocean and the possibility of life. Neptune, by contrast, is remote, distant, difficult to reach, and currently provides no obvious incentive for a new mission. There is no suspected life on Neptune or its moons, at least not in the forms that would be most interesting to detect with current technology. There is no resource extraction potential. There are no human colonies to support. Neptune is, from a pragmatic perspective, not particularly important. And yet Neptune is important from a scientific perspective. A new spacecraft to Neptune would face enormous challenges. The journey time would be measured in years, perhaps over a decade depending on the specific trajectory chosen. The spacecraft would need to carry power sources capable of functioning far from the Sun, where solar panels would be useless. It would need computers and instruments designed to survive the radiation environment surrounding Neptune. It would need thrusters and propellant to slow down when approaching Neptune, to match orbits with the planet, to perform the complex maneuvers necessary to study the system. It would need sufficient data storage to record observations and sufficient communication systems to transmit information back across billions of kilometers of empty space. It would need to be designed for reliability and an environment where no repair or servicing is possible, where failure would be permanent. The cost would be enormous. The mission would likely consume a significant portion of any space agency's budget for a decade or more. The return on investment would be scientific knowledge, understanding of how planets form and evolve, data that would advance fundamental science but would not directly benefit anyone on Earth. In an era of tight budgets and competing priorities, missions to Neptune are difficult to justify politically or financially. Yet proposals for future Neptune missions do exist. Scientists continue to develop plans, to refine mission designs, to argue for the scientific value of a return visit. One recent proposal suggested a spacecraft that would arrive at Neptune, deploy a probe into the atmosphere to measure composition and temperature, and then pass by Triton to gather detailed images and data about that frozen moon. Another proposal advocated for an orbital mission, a spacecraft that would arrive at Neptune and settle into a long-term orbit, years of observation rather than a brief encounter. A third proposal suggested a Triton-focused mission, a spacecraft designed specifically to study the captured moon, to determine the mechanisms driving the geysers, to measure the composition and geology in detail. All of these missions would cost billions of dollars. All would require years of planning and preparation. All would involve enormous technical challenges, and none of them are currently funded or scheduled. The last visit to Neptune remains Voyager 2's 1989 encounter. No new mission is in development. No funding has been allocated. No launch date is scheduled. Neptune waits, continuing to orbit the Sun at its vast distance, continuing to change and evolve with the passing seasons, continuing to radiate its mysterious excess heat into the darkness of space, waiting for the next human attention that may not come for decades or centuries, or possibly never during the remainder of human civilization as we currently know it. Yet Neptune remains important from a scientific perspective. Neptune represents an entire class of planets, the ice giants, of which we have extremely limited knowledge. Neptune is the archetype of that class, the best studied ice giant, and it remains largely mysterious. Understanding Neptune would advance understanding of ice giants throughout the universe. Astronomers have discovered thousands of exoplanets orbiting distant stars. Many of those exoplanets appear to be ice giants, massive worlds far from their parent stars. Understanding Neptune, an ice giant in our own solar system, would provide crucial information for interpreting observations of those distant worlds. Without understanding Neptune, the study of exoplanetary ice giants remains incomplete, limited, unable to reach its AF-UL potential. Neptune, in context, compared to Uranus, is perhaps the most scientifically useful comparison. Uranus and Neptune are ice giant twins, formed in similar locations, from similar materials, subject to similar processes, yet they differ significantly in many properties. Uranus is colder internally than Neptune. Uranus's magnetic field is more tilted than Neptune's. Uranus rotates with a rotation axis tipped almost 90 degrees, so extreme that the planet essentially rolls like a ball through space rather than spinning like a top. Neptune rotates more normally, with a tilt of about 28 degrees, similar to Earth's rotation. These differences in such similar planetary bodies make Neptune and Uranus into a natural experiment, a comparison that reveals how initial conditions, formation location, migration history, and post-formation evolution can alter planetary outcomes, even when starting conditions are similar. Understanding why Neptune and Uranus are different would advance understanding of planetary processes generally, explaining how planets evolve, how they change, how they become what they are. The differences extend deeper than surface-level observations. Uranus's magnetic field, while tilted, is relatively weaker than Neptune's. Uranus's winds are less violent, less energetic than Neptune's. Uranus's interior is less active. The rotation of Uranus is unusual for another reason beyond its tilt. Uranus rotates backwards relative to its orbital motion. The planet orbits the Sun in one direction, but it rotates on its axis in the opposite direction, as if it had been knocked over billions of years ago and never fully recovered its original orientation. Neptune, by contrast, rotates in the normal direction, matching the direction of its orbital motion. This difference suggests different histories. Uranus might have experienced a violent collision billions of years ago, an impact so severe that it knocked the planet over sideways. Neptune might have avoided such a collision, preserving its original orientation from the time of formation. These details matter because they affect how the planets evolved, what their internal structures are like, how they should be expected to behave. Yet the cause of these differences remains mysterious, unclear, not fully explained even after careful study. Neptune's system of moons and rings, considered in context with other planetary systems, reveals patterns. Saturn's rings are spectacular, bright, composed of clean water ice reflecting sunlight. Jupiter's rings are dark, faint, composed of dusty material. Neptune's rings are also dark, dusty, similar to Jupiter's rings. Yet Neptune's rings also include the mysterious ring arcs, incomplete rings that persist in unusual configurations despite the laws of orbital mechanics suggesting they should disperse. These ring systems tell the story of planetary history. Saturn's bright rings might indicate relatively recent origin, perhaps from the disruption of a moon or the capture of a passing comet. Jupiter's dark rings might indicate origin through different mechanisms, perhaps from dust ejected by collisions on small moons within Jupiter's system. Neptune's dark rings with their mysterious arcs might indicate a complex history, possibly involving the capture of Triton and the gravitational disruption that accompanied that capture, possibly involving relatively recent collisions that generated new material, possibly indicating a system in transition, a system actively changing and evolving. Triton, in particular, stands out as an anomaly among planetary moons. Most large moons orbit in the same direction as their primary planet rotates, in what is called a prograde orbit. Triton orbits backwards, in what is called a retrograde orbit. Triton is the only large moon in the solar system to do so. This retrograde orbit is almost certainly the result of capture, an event billions of years in the past where Triton was a free-ranging Kuiper Belt object that wandered into Neptune's gravitational influence, was captured into orbit, and has remained bound to Neptune ever since. The capture of Triton would have been a violent event, dramatically altering Neptune's system, perhaps creating the rings through gravitational disruption, perhaps creating the current configuration of moons through redistribution of material. The gravitational shaking from Triton's arrival might have knocked other moons into different orbits, might have created collisions that generated dust and debris. The system that we observe today might be fundamentally different from what it was before Triton arrived. The capture of Triton is not ancient history. It is not a minor side note. It is a defining event in Neptune's history, an event that shaped the current system and continues to influence it through the tidal forces that are gradually spiraling Triton into Neptune. Triton's inward spiral is inexorable. The math is clear. The orbital decay is certain. In approximately 3.6 billion years, Triton will pass within Neptune's Roche limit and be torn to pieces. The fragments will form new rings, a replacement for the current faint rings. The rings will be brighter than Neptune's current rings, perhaps more impressive, perhaps more reminiscent of Saturn's spectacular ring system. This future transformation is mathematically certain, even if it remains billions of years away. Neptune's future is written in the fate of Triton, a doom that is guaranteed by orbital mechanics, an event that cannot be prevented or avoided. This future-written nature of Triton's fate is perhaps the most poignant aspect of Neptune's system. Triton knows its end. The mathematics that governs gravity dictates that Triton will be destroyed. The process is already underway, has been underway for billions of years, will continue until Triton reaches the fatal distance. Neptune will destroy its largest moon and inherit new rings. The rings will evolve over billions of years more, particles gradually falling into Neptune's atmosphere, gradually dispersing, slowly being removed from the system. And eventually, in the incomprehensibly distant future, Neptune's ring system will disappear. The planet will lose its rings and be left only with its remaining smaller moons, distant companions orbiting a world that has fundamentally changed from what it is today. Neptune's history is far from over. The story continues to unfold at timescales that make human civilization seem insignificant. Neptune is a world with a deep past, a mysterious present, and a mathematically defined future. It is a world worth understanding, worth studying, worth returning to despite the distance and difficulty. It is a world that reminds us how much we do not know, how many mysteries remain unsolved, how vast the solar system is, and how limited our direct knowledge of it truly is. Neptune waits at the edge of human knowledge, a distant ice giant orbiting the sun, changing slowly with the passing seasons, radiating its mysterious heat into the darkness, a world that continues to puzzle and intrigue, that continues to hide its secrets despite centuries of observation and a single brief spacecraft visit.